So we have seen that when two players are playing and both of them have a dominant strategy, the question becomes, what next? In the previous one, you see that Husseini has a dominant strategy. You also notice that Chia has a dominant strategy. So that takes us to the level of equilibrium. Now in game theory, there are several kinds of equilibria. We shall look at only one of them. I told you that we are looking at the basics. There is the pure strategy Nash equilibrium. It's one of the equilibrium. The pure strategy Nash equilibrium. There is also the mixed strategy Nash equilibrium. And then there is the sub-game perfect Nash equilibrium. And then there is the Bayesian Nash equilibrium. And even they have the Bayesian sub-game perfect Nash equilibrium and all that. But we're going to look at this one of them, the pure strategy Nash equilibrium. It's a basics for normal form games. It was under the auspices of John Nash. Remember Professor Nash? I've told you to watch the movie known as A Beautiful Mind. When we say a pure strategy Nash equilibrium, or sometimes people just say Nash equilibrium, but I want to be specific here. It is a strategy where we are talking about the best response behavior for that matter. It happens when each player is satisfied with the choice that she took, given what the opponent is choosing. So you can see that given the opponent's decision, the player's choice is he's okay with it. I'm okay. I'm okay, giving the choice of that guy's decision. And this is an important area here, okay? Because the choices are critical. They are critical in determining what action the person is going to take. Okay, so let's get some few things clear. So if I am selecting mango and you choose pawpaw, I don't care whether you choose pawpaw or you don't choose pawpaw. I am stuck to my mango. And the other guy said, I also don't care whether you choose mango or not. I'm stuck with my pawpaw. Okay, you are happy with your pawpaw and I'm happy with my mango. We are both having our dominant strategy. And so that means that we are good to go. So the two players, both of them have got their dominant strategy. Then both of them are good to fly along. The question, however, is how do we arrive at this pure strategy Nash equilibrium? There are three ways. There are three approaches to arriving. One of them is obvious. The first one is when both of them have got dominant strategy. And this approach is known as the dominant strategy equilibrium. So when two players, both of them have got a dominant strategy, okay, then that becomes the pure strategy Nash equilibrium. That becomes a Nash. So a dominant strategy Nash equilibrium is always the Nash equilibrium. There's another one approach which can lead you to arriving at the pure strategy Nash equilibrium. And this is known as the iterative elimination of strictly or weakly dominated strategy. And there's a final one which is known as the best response strategy. We're going to look at each one of them in this context. So let's go back to the prisoner's dilemma. Okay, let's look at this prisoner's dilemma now. In looking at the prisoner's dilemma, can you tell me, since both of them have got a dominant strategy, the question is, what is the pure strategy Nash equilibrium? Who can tell me? It's very simple. What is the pure strategy Nash equilibrium here in this? Well, remember, Husseini had a dominant strategy which was complex, isn't it? Chia had a dominant strategy which is complex. And whenever two players, both of them have got dominant strategy, we don't even question. Then the pure strategy Nash equilibrium is they are both dominant strategies. So the pure strategy Nash equilibrium here is for both players to confess, and get 6-6. Just finish. Any question on that? It's a very simple one. Okay. Both of them get 6, 6, and we are good to go. Now, there is a concept that we are going to look at here. It's an interesting concept that is connected to the Nash equilibrium. And this concept is known as the concept of Pareto optimality. Some of you have heard about it. A Pareto efficient outcome. Let's take an outcome, which is O star. That outcome is said to be Pareto optimal if there is no outcome that Pareto dominates it. An outcome is said to be Pareto optimal if there is no outcome that Pareto dominates it. So let's take an example. Can some of the outcomes of a game be better than another? Of course. I just showed you outcomes A, B, and C, and you realize that some of the outcomes were better than the other. Take, for example, this outcome O, which is 7, 8, where you have 7 units of the utility for the player 1, and the player 2's utility is 8. If you look at this outcome, compare it with the outcome O prime, which is 7, 2. You can see that for player 1, he doesn't care. He is okay with whether you take O or O prime. But for player 2, you can see that player 2 makes this outcome O at least. The word at least is important because of the 7 and 7 for both. It makes the outcome at least as good as, for everybody than for the O prime. The reason is because it is equal for player 1, but strictly better for player 2. So we can say that outcome O Pareto dominates outcome O prime. So even though O prime has got the same number, which is 7 and 7 for both, okay, even though it's got the same number, that outcome is Pareto dominated. So O prime is Pareto dominated. And so O Pareto dominates O prime. So when do we say an outcome Pareto dominates another outcome? Well, an outcome Pareto dominates another outcome if that outcome itself is not Pareto dominated by any other outcome. I want to repeat that. An outcome is said to be an outcome that Pareto dominates another outcome if this outcome in itself is not Pareto dominated by another outcome. Does it make sense? Let's take some examples of Pareto domination here, okay? When we use those examples, it might make sense. So let me ask some very tricky question, and I will need you to give me some answers by raising your hand, okay? First one is this. Can a game have more than one Pareto optimal outcome? If you don't get it, let me go back to the definition and explain it to you. But can a game have more than one Pareto optimal outcome? Stephen.
God, please, no.
Why? You can't just say no.
Yeah, because from the definition we had, we said that the Pareto outcome does not have any other dominant pair of Pareto in it.
So, but I
so
can have
that's
A,
what I'm thinking,
I can
please.
have A, and A is not dominated by anybody. And I can have B, that is also not dominated by anybody, can't I? If you go back to this example, if you go back to the example that we have here, okay. If you go back to this example, let me just give you some scenario here. Let's say that this value here is 7. Let's say that this value here is 7. Would you say that C dominates B? Does C dominate B? Does C Pareto dominate B? Now, anytime you are looking at Pareto optimality, look at who is dominating me. If nobody is Pareto dominating me, then I am Pareto optimal. You get that point? If nobody is Pareto dominating that outcome, then that outcome is Pareto optimal. So if you look at A, let's start with A. A is Pareto dominated by B. A is also Pareto dominated by C. So A is not Pareto optimal. Look at B. B is not Pareto dominated by A. We know that for sure. Look at B again. Okay. B is not Pareto dominated by C. You see, in one way, from the player 2 perspective, okay, 9 is better than 7, but then the 7 here on the C is not better than the 8. And once you are not better in all angles than this other person, you say you don't Pareto dominate, at least in all angles. Okay, but if this one had been 8, then we can say that B is Pareto dominated, but that one is even weakly. So B is not Pareto dominated by C here. And C is also not Pareto dominated by B, because he's better in one, but not no worse off than the other. And that is a principle of Pareto optimality. So you can have a situation where there are more than one Pareto optimal outcomes. Okay. That's it. You can have more than one Pareto optimal outcome, because if all the payoffs of 2 outcomes are the same, do you see even the trickiest one? All the payoffs of 2 outcomes are the same. They are all 6, 8, 6, 8. Then neither will Pareto dominate each other, and therefore they will all be Pareto optimal. Morrison, does it make sense?
Yes, Doc. Yes, please. Thank you.
Let's go to the next one. Does every game have at least one Pareto optimal outcome? Does every game have at least one Pareto optimal outcome? What would you say? What would you say? Does every game have at least one Pareto optimal outcome? Is a yes or no? Mark?
Let me try this. I think it will be a yes.
Why?
Because at the end of the day, there will be a final denominating outcome that will denominate over the rest of the denominated strategies.
Okay. So if there is no Pareto, let's assume that what the question is, if there is no outcome that is Pareto optimal, because for you to be Pareto optimal in the first place, you must Pareto dominate somebody, isn't it? So when you say, does every game have at least one Pareto optimal outcome? At least one Pareto optimal outcome. There cannot be a situation where there is no at least one Pareto optimal outcome, because other than that, nobody will be Pareto dominated. And for you to be a Pareto optimal outcome, you must Pareto dominate another. Now, if all of us say that nobody is Pareto dominated, so there is no Pareto optimal. Now, first of all, how did you know that nobody is Pareto dominated in the first place? For you to know that nobody is Pareto dominated means that in the first place, you agree that somebody is Pareto dominated. So yes, every game has to have at least, you are right, every game has to have at least one Pareto optimal, because this is because in order not to be Pareto optimal, okay, it has to be dominated by another. For you not to be Pareto optimal, somebody has to dominate you in the first place. And so that is a picture being painted. Okay, let's go to the interesting part here. Now, the pure strategy Nash equilibrium, if you can remember, it will usually fail to imply Pareto efficiency. And the reason why this is so is that in games where there are many externalities, that the players fail to internalize the externalities, it can cause that. I'll give you an example. I'm not going to treat externalities now, but I'm going to just give you an institute. Do you realize that the prisoner's dilemma that we considered, that prisoner's dilemma, both players have their dominant strategy. And so those dominant strategies became the pure strategy Nash equilibrium. All right, so now we have the pure strategy Nash equilibrium. The question now is that because we had, even though we had a pure strategy Nash equilibrium, that Nash equilibrium wasn't the best. Do you guys realize that? It was 6-6. Do you remember it was 6-6? But the better outcome would have been what? 1-1. 1-1 is short sentence for both of them. But eventually, the equilibrium was 6-6. Okay. And that is because of what we're about to look at now. So let's look at what we're about to look at now. Is there a Pareto optimal outcome in the prisoner's dilemma game? Look at the prisoner's dilemma game now. Look at it. Please, before you can determine whether there is a Pareto optimal outcome or there is none, you have to take each one and consider whether it is dominated by, Pareto dominated by any other one. So would you say there's a Pareto optimal outcome? Let's take outcome number 1-1. Okay, take this outcome 1-1. If you look at this outcome 1-1, what would you say? Is it Pareto dominated by another outcome? That outcome 1-1, is it Pareto dominated by another outcome? What do you say? Yes, that outcome, if you look at it carefully, okay? If you want to go by higher levels, if you look at it carefully, or if you want to go by lower levels, okay? If you want to go by lower levels, you will notice that that outcome, let me use higher levels. If you look at this outcome, 6 and 6, Pareto dominates it. Do you realize that 6 and 6, Pareto dominates 1 and 1? Because 6 and 6 are higher than 1 and 1. So we can say that outcome 1 and 1 is not Pareto optimal. Let's take 6 and 6. Now we can see that when you take, and I didn't even want to check the other 0 and 15 because once the 6 and 6 Pareto dominates 1 and 1, I can quickly say that 1 and 1 is not Pareto optimal. So that's why I didn't want to go to the next level. Okay. Now let's take the next thing. The next thing is 6 and 6. Would you say 1 and 1 Pareto dominates 6 and 6? No. Would you say 0 and 15? Does it dominate 6 and 6? Well, 15 dominates 6, but the 0 doesn't dominate the other 6 for the red one. And so we can still conclude that it is not dominated by 0 and 15. What about 15 and 0? Well, 6 and 6 is not Pareto dominated by 15 and 0. So on the basis of this, we can say that 6 and 6 is Pareto optimal. 1 and 1 is not Pareto optimal. We concluded that. Now let's go to 15 and 0. 15 and 0 is not Pareto dominated by 1 and 1. Because even though 1 is, what do you call it? This one, black one, is bigger than the 0, okay? The other one is not bigger than the 15. Okay? The same way is not Pareto dominated by 0 and 15. And it's also not Pareto dominated by 6 and 6. It's not. And so we can say that 15 and 15 is also Pareto optimal. And the same way we can say that 0 and 15 are also Pareto optimal. In fact, I want us to look at them in terms of negative values instead of positive values. So I'm going to go back and switch my sentence I said here. Okay. When I said I was using positivities, okay, let's consider them as negative so that the smaller value is better because we are talking about jail sentence. Okay. So when you look at it in terms of jail sentence, we can now say that if you look at 1 and 1 compared to 6 and 6, if you look at 1 and 1, 1 and 1 jail sentence is better than 6 and 6 jail sentence. And so 1 and 1 is Pareto optimal compared to 6 and 6. And 0 and 15 jail sentence is not Pareto dominated. This 0 and 15 and 0, none of them is Pareto dominated by anybody. But we can say that 1 and 1 jail sentence is better than 6 years jail sentence. And so 1 and 1 is Pareto optimal. Now, 1 jail sentence, I'm comparing this one and then the 15. 1 jail sentence, okay, if you look at it, 1 and 1. Okay. This one, I'm just comparing the 1 and 1 with the 0 and 15, just to prove a point, okay, with this 0 and 15. If you look at it, 1 jail sentence, 1 year is not better than 0, okay, but 15 too is not better than 1 year. Okay? That is why I'm saying that the 1 and 1 is Pareto optimal. So in switching it, 0 and 15 is Pareto optimal, 1 and 1 is Pareto optimal, and then 15 and 0 is also Pareto optimal. 15 and 0 is also Pareto optimal. So on the basis of this, we can say that 3 of them are Pareto optimal, but 6 and 6 is not Pareto optimal because it's not better than anybody. So we can now say that all of them are Pareto optimal, but only 6 and 6 is not Pareto optimal. Now the word Pareto is social. So when we say it's not Pareto optimal, what we are saying is that it's not socially good. Now, do you remember that this was the one that was selected? Do you remember? This was the one that was selected as pure strategy Nash equilibrium. And so it means that the players were being selfish. They were all trying to assume that the other one is going to lie and get the jail sentence. So there was a tendency to cheat. And because there was a tendency to cheat, even though it is Pareto strategy, Pareto, what do you call it? Pure strategy Nash equilibrium, it was not Pareto optimal. It was Pareto inefficient. It was not Pareto efficient outcome. And this is what we call the paradox of the prisoner's dilemma. The prisoner's dilemma is one strange situation where the equilibrium is not Pareto optimal. The equilibrium where both of them eventually landed is not Pareto optimal. It's not socially good for all of them. And there are certain things, when we say something is Pareto optimal, it means that all of us, it benefits all of us. Social good is like street lights and all of those things. You know, it's for all of us. All of us are benefiting. But because these players were being privately dependent, they were dependent on their private gratification, okay, eventually the choice of 6 and 6 did not end up well for all of them. So the best outcome would have been 1 and 1, if you can remember. 1 year jail sentence, not confessing. If Chia had decided not to confess and Husseini has decided not to confess, then that's it. The prosecutors will not get them. But because of that tendency to cheat, they rather decided to confess, hoping to cheat the other, but eventually they cheated themselves. And so they end up getting 6 jail sentence. Pareto optimality. These are some examples of Pareto optimal outcome I want us to consider finally. The first one, which of these payoffs is Pareto optimal outcome in these 4 games? So we are going to look at the first one here. This first one here. Which of them is Pareto optimal? Well, if you take 1 and 1 here, which outcome dominates it? 0, 0, no. 1, 1, no. So no outcome dominates 1 and 1. So we can say that this 1 and this 1, This is Pareto optimal. And we can also say that this one too is Pareto optimal because it's also 1 and 1. Now let's look at, so that's this one. Let's take this outcome on the right here. Who can tell me which of the outcomes is Pareto optimal? Which of these outcomes is Pareto optimal? Let's take 2 and 1. 2 and 1 is not dominated by 0 and 0. And we are looking at it in positive terms. Okay. It's also not dominated by 1 and 2. Because even though this 1 here isn't, 2 here dominates the 1, this 1 here doesn't dominate the 2. So 2 and 1 is Pareto optimal. It's not dominated by anybody. Now, of course, we can see that the 0 and 0 are dominated by the 2 and 1 and then the 1 and 2. So on the basis of that, we can also say the same thing about this one. This one too is the same. Okay. Pareto optimal outcomes. Oh, where is it? Okay, so that's it. So we've been able to conclude that this and this, that's the answer that you see on the right here. And let's go to the next one. Let's go to this one, which is head and tail. Head and tail. Take 1. Take 1 here. Okay, and a negative 1. Which outcome dominates it? Nobody. Nobody will dominate it because this one is better than this negative one, even though this one is also better than this negative one. And it goes against. This is a typical example of a zero-sum game. You will learn it later. This is a typical example of a zero-sum game. Nobody dominates it. So all of them are Pareto optimal outcome. This outcome is Pareto optimal. This outcome is Pareto optimal. This outcome, nobody dominates it. So all of them are Pareto optimal outcomes. Now, keep that in mind, okay? And that's this. So you can see that those that I've circled, all of them are Pareto optimal outcomes. Now the final one. This is the last one, the C and D, and this is the C and D here. Now let's compare this negative 1 and this negative 1, this outcome. This outcome, if you look at them, which outcome dominates it? Well, negative 1 and negative 1 is better than negative 3 and negative 3. Okay. Now, negative 1 and negative 1 is not better than 0. It's not better than negative 4 and 0 because 0 is better than negative 1. But the negative 1 is also better than negative 4. So I can say that this one doesn't dominate it. The 0, 4, 0, negative 4 doesn't dominate this outcome CC. The negative 3, negative 3 doesn't dominate the negative 1, negative 1. So negative 1, negative 1 is a Pareto optimal outcome. Now, which outcome dominates this? No outcome will dominate it. Because the 0 is better than negative 1, but the negative 1 is better than negative 4, and it goes against it. So the same thing, this one to no other outcome dominates. But this 3, negative 3, negative 3, it is Pareto dominated by negative 1, negative 1. So this is a typical example of a kind of a prisoner's dilemma. Okay. So on the basis of this, which of the payoffs here is Pareto optimal outcome? The ones I've highlighted, all of them are Pareto optimal except the negative 3, negative 3. Because that one is Pareto dominated by negative 1, negative 1. And this is the answer that you see here as well. Pareto optimality is a very powerful concept that you want to appreciate and you want to understand. On this course lecture here, you can find some of these examples, and then you can find examples of Pareto optimal outcome. Pareto optimal outcome, it helps you to be able to know which outcome is socially beneficial. But when an outcome is not socially beneficial, what it means is that it's privately beneficial. It's private. It's beneficial, but like the prisoner's dilemma, it was privately beneficial to each one of them, but it wasn't socially beneficial. 1 year jail sentence was better than 6 years jail sentence. Next time we shall look at a zero-sum game, and then we shall look at the other 2 approaches of determining the pure strategy, Nash equilibrium.